Should I start? That bodes well.
Dramatic start.
All right, hello. I'm Brian O'Mara. I work here. Today I'm going to talk about likelihood and Bayes. Okay? But because it's late in the day and stuff, we're going to have gambling. Okay? So for this. So I have a coin, and I flipped the coin and gotten this distribution. Heads, heads, tails. Okay. And what I need to do is guess on the next 18 flips, how many heads will I get? And I want you to take your sticky notes I handed out to you, write your name and your guess on the piece of paper. And there's no game theory here, so if one person wins or if all of you win, it's the same amount of candy. So I'm trying to pick the unpopular ones so you can, no game theory, just you're the only one playing this game. So think about what your guess is and why you're making it. And also, I mean, this workshop's for you all. So if you have a question during it, interrupt me, ask questions. Okay, that's why we're here to teach you. Is everyone written down a guess? Okay, pass it over to the end, and Joseph, could you collect it? Thanks. So there'll be 18 more flips. How many are going to be heads? From 0 to 18. Okay. Sorry. Okay. So first, a little context. So why are we doing all this? Right? Why are we talking about likelihood and Bayes? Well, for all of the methods we've been talking about, to actually get inferences, to make choices between models or to make guesses about inferences about parameters, we need to have some sort of model, some way of evaluating models. Okay, and likelihood and Bayes are two related ways we look at data to understand the processes underlying them. Okay. So what does this all mean? So let's think about probably getting heads. Could you? Yeah. Right. So let's think about a simple binomial coin flipping example we all know and love. Okay. So probably getting a single heads given probably if heads is p is just p. Right? Not hard. Okay. This is a probability, so it goes from 0 to 1. Right? So those are the range. We're not there. We're in 0 to 1. Basic stuff. Probably getting 2 heads. It's p squared. Probably getting heads, and probably getting heads again. Okay. So here is that surface. Okay, so probably getting 2 heads is that. And so when I'm looking at talking about this, is saying it's the probability of the data given p. It's probably of having 2 heads as the data given p is p squared. Okay. Another notation for it, probably of data given p is p squared. And thus, the likelihood of p given the data is probably the data given p, which is p squared. So that's all likelihood is. Whenever you're doing the likelihood in any method, is to tell you the probability of the data. Okay. Now if we get numbers that are sort of funny, like -500, that's not a probability. Right? We'll talk about what that means in a little bit. But in general, likelihood is just the probability of the data. Okay. Any questions about that? Okay. And of course, this depends on the data. Right? So here I have 3 possible data sets I could have from my coin flipping example. 2 tails, 2 heads, heads and a tail. Describe the distributions. What do you see here? Probably, yeah, actually probably is, yes. Good. Okay. Good. What else? Right. So it's symmetrical with respect to P. Why isn't 2 heads symmetrical with respect to P? Right. So as P increases, the probability of getting 2 heads should increase. So that's why it's increasing that way. Good. Okay.
Because tails or heads.
Heads. Now here I have another data set, like we had with our case. Okay, so here's our data set, and here's the likelihood surface for our data set. We have 2 heads and tails. Okay? So that can be, we can actually visualize the surface, right? This is the likelihood surface. And so maximum likelihood, I'm going to find what the maximum value is there. Right? And that's the maximum. Right? So we're talking about, you want the maximum likelihood estimate, right? It's where this peak is highest. Okay? And we have various ways of figuring that out. We can do an optimization approach. We can try just doing brute force and say, let's try this value, this value, this value. And here we plot that curve. But whatever we get, the peak is here. Beautiful. Right? 2/3. Right? So in our case, 2/3 of 18 is 12. If all of us understand maximum likelihood well, we'll have a lot of values at 12. Okay, so we have some here, right? But we have a lot more at 9. Are these people stupid? Yeah, can I do math? No, right? They're doing something else here. Right, so here's the MLE, here's some other solution, and here's the other people who are doing other things. Okay? As we say in the South, bless their hearts. Okay, so maximum likelihood. Yeah. All right. So here's an example of this. Okay. So here we have continuous traits, and here we have beat depth in finches. Okay. Classic grant work. And here is Brownian motion, and here is various rate parameters of Brownian motion. Here's likelihood of each. And maximum is right here. So that would mean the maximum likelihood estimate for that Brownian rate parameter is around 0.15 or 1.7. Okay. What does it look like in real life? So as Marguerite shows how we can do, we can take the value of starting state and then try simulating many, many times to see what we come up to. Right? So here we have this distribution for this rate. Okay. This for up here. This for up here. Okay. And so with the coin flipping example, I can tell you exactly how often we're going to get exactly 2 heads and 1 tail. It's a discrete number. Right? How about beat depth? I'm going to tell you they're probably getting exactly 1.333412555 millimeters for the beat. Right? Granting infinitesimal likelihood. Okay? Same when you get a PDF for normal, right? Probability density function, the same thing for likelihood. Okay? So even though it's a continuous variable, it's still likelihood for it. Okay? One thing that tricks up people here, though, is that probability can be greater than 1. Right? So the area under the curve is 1. Right? But the height of the curve could be higher than 1. Because it's all rhythm. Right? It's still fun. Still bad. Any questions about that? Yeah. Mike.
So there you're just simulating some rate, right? So
yep. Yeah. And had I chosen a rate that was too small, right, then my observed beat depth would be way out here. Then my distribution would be power. So the probability of getting that beat depth would be really low. Right? But if you make it too wide, high probability of getting things that are higher than 2. So some rate that maximize the chance of seeing that particular beat depth. And that's what we're showing with this. So, other questions about this? Okay. So why likelihood? So some of the properties of likelihood. So likelihood is consistent in the correct model. Right? So an old classic paper about the Felsen sign right? Show that likelihood to get the right Sherwin price when you couldn't, if you have the right model. Later can show that if you get the wrong model, sometimes likelihood can fail. It's efficient. What does that mean? It gives you the best estimates for the amount of data you have. Okay? This is in a world where we have 38 species. Efficient estimators are nice. A problem with it is it can be biased. But this bias decreases with sample size. So it's still more powerful than unbiased estimators, which is what we use. There are unbiased estimators we use instead. One practical problem is that likelihoods can get really, really small. Okay, so here's our coin example again. So one throw, one heads, likelihood is 0.5. That's fine, you can put it in the computer. 5 throws, 0.3, 3 throws, 25 heads, this, 500, 150, this number. Okay. Your computer has finite precision, an R. And so after a while, if you get that number too small, you could say, take a number and then subtract a little bit from it. Are these equal? And your code will say, yes, they are equal. It doesn't have the resolution to tell them apart. And if you can actually see this, if you want to, you can enter this command in R, and it'll tell you the precision of different numbers. And so in phylogenetics, you often get numbers that are really, really small. There's the probability of having exactly A, T, 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 C, 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 G, G across hundreds of species on a tree. Very, very small. You have to get exactly that set of bases. And so it becomes a number that's too small to put in the computer easily. So what we do with that then, I'll check it before we give out the prizes, don't worry, is do log likelihood. So put on a log scale, it's easier to deal with. These funny numbers that have negative values, so likelihoods, that's what log likelihood is. So you could take exp of this, you get back to these numbers. Remember, the sequence is too small, that's what it is. So we see likelihood values that are negative 0.4. No, we don't see negatives, we'll say negative log likelihood. Yeah, sure.
Just a comment, sometimes people are worried. Sometimes people are worried that, gosh, the likelihoods are so small, or the log likelihoods are so negative. What that actually means is you've got a lot of data. There's a lot of different possible data outcomes, and you've got none of them. So it's a good thing, not a bad thing. It's only a problem if it's much smaller than what you could get under some other hypothesis.
Right. That makes sense to people? So now we have a likelihood for one model. How can we tell if one model is better than one model? Well, there's several approaches we can do. Okay. One is likelihood ratio test. Who's heard of this? Perfect. So the issue with this is models have to be nested. So one has to be a restriction of the other. Right, so if I have a cumulative process, and one of them has 2 different thetas, and one has 1 theta, right, if I can reduce the 2 theta 1 to the 1 theta 1, those are nested models. Okay? If I have a model where I have a one back with 2 thetas, and then Brownian motion with a trend, those one can't be reduced to the other. They're not nested with each other. They're nested within some other model, but not within each other. You can't do a likelihood ratio test for that. And so the classic model test, or J-model test for comparing nucleotide models, that was what we initially do is we compare nested pairs of models and work down. This isn't used much anymore because of the disadvantages of this nesting. So instead what's most common is AIC. It's called the Akeke information criteria. This represents how much information is lost about the truth by using your model. Now, as the AIC is relative AIC. That's like saying, how close are we to New York? Well, I don't know how close we are to New York, but she's about 10 feet closer than I am. And so use these relative AIC measures. Okay? And there's a great line, so Bergman and Anderson wrote a canonical book about this. There's a great line where they say, deriving this, the truth drops out as a constant. Okay? So you don't need to have the true model in your set. In many cases, we think the true model isn't in our set. Right? So comparing one-rate Brownian motion to two-rate Brownian motion, what's the odds that mammals have one parameter or two parameters governing their body size? Pretty low. Right? So the true model is way out there in complexity. What we're doing is we're saying, which of these bad models we have is the least bad? And AAC tells us this. And there are rules of thumb about this. And you can see they're very ad hoc. Right? So if two models are within two AAC units of each other, they're both pretty good. Okay. If one is 4 or 7 worse, there's really less support for it, or which has essentially no support. And again, this depends on your data set size. Okay. So a lot of the comparative methods we've been doing, oftentimes the models are in this range. Brownian motion, back, all your data is in this range. Okay. So I'm not super confident that I'm rejecting them. The other thing in the AAC world is you don't reject models, you're just looking at different support for them. Okay. So it's not like you don't get a p-value, you don't say, now I can loosely reject this model. So there's a lot less support for that model. Other questions about AAC? Okay, here's an example from a very good paper a while ago. Okay, looking at various uncertain vector models. And so they tried a Brownian motion model, and an OU with 1 theta, an OU with 3 thetas, 4 thetas, and an OU with multiple thetas. And so you can get parameter estimates. Okay? Here are the maximal estimates of the parameters. And they also get the delta AIC. Okay? And then you can get relative likelihood, and from that the weights. And they feel sort of like posterior probabilities, they're not. You sort of treat them in sort of similar way. It's sort of, here I have a lot more weight for this model, 80%, than for this model, 0%. But 87% isn't slam dunk. You can't ignore the information that models are giving us. So what do? What you do here is do model-weighted parameter estimates. Okay. So here I say, okay, here's the distinct sigma, right? This row right here. So all the models have a sigma. Okay. So I want to get the best estimate of sigma, I want to combine it multiple models to do it. So that's okay. So this model says sigma is 0.21, it only has a weight of 0.03. There. So it's weighted average. This can be nice for models where we have some models have a parameter, some models don't have a parameter. Right? So we could treat, BM as having an alpha parameter of 0, and this one had an estimate of 0. If you want to say how important is this alpha parameter in the models, I can get a weighted average of alpha across all the models. So those with it set to 0, those without it. Give an estimate of what it is. Yeah. Oh, yeah. Okay. They come from the relative ratios, the relative likelihoods, which come from the AIC, from the delta AICs. So the actual calculation is you take the delta AICs and then it's exponential negative 2.5 times that. That gives you the relative likelihood for each model. And you just sum them up and divide each one by that sum. Okay. Other questions about this? One thing we often do in comparative methods, we have these fights about, sometimes people care about, is OU or BM the best model? Right? So people argue, compare the delta ACs and see which one's better. And that's good. It doesn't want to go and look at the parameter estimates. Because we have a large enough data set, we're going to pick a more complex model. Right? So I say, I have 1,000 taxa, and OU is much better. What's your alpha parameter? Alpha is 0.00001. Phylogenic half-life, it'll take 1 billion years to get to the optimum. But it's an OU model. Yes, it is, but we're going to realize that it's not accurate, it's very strong. It's look at the values. Last time we taught this course, we had an instructor who was very good at showing that these actually have parameter values. These are actually units of body length, or body length. It's important to keep that in mind when thinking of these forms. These are actually measurements. Any questions on that? All right. So, some of you guessed 12, but between these in the line. Right? Many of you didn't. So what are you doing here? What's your brain doing? You should guess a different number. Well, this comes from conditional probability. Here's the cartoon. You can look at it. You can read it. This is basic laws of probability, right? So probably if A given B is probably B given A, so right? So that's fact. That's just looking at Venn diagrams. What we do with Bayesian is convert the labels. So probably a hypothesis given the data, probably the data given the hypothesis, probably the hypothesis, probably the data. So that's Bayes' rule. So this is not controversial. Because it's controversial about whether it be a Bayesian or frequent test, and we get into fights sometimes, right? But it's not over whether this is true. This is fine. The question is what we should do with this. And so here's Bayes' rule again. So we call this the posterior probability. That's what we get out. And this is actually a very nice term, right? Because when you have this, you can say, okay, the probability of this hypothesis being true is 45%, 95%. Which feels very good to us as scientists. Right? So this is very appealing. This is our friend, the likelihood. Calculate Braggs ways. This is the prior. We'll talk a little bit more what that means in a little bit. Okay. And this is the probability of the data over any hypothesis. Okay. So one way to do that is to calculate the likelihood over all possible hypotheses and add them up. Okay. That can be hard given hypotheses, like for example, the size of tree space. Okay. And so we have algorithms to deal with that too. Okay. The real crux of the problem is this prior. So the prior is when you first approach the problem, knowing nothing else, okay, what's your estimate? Right? So I said to you, I'm going to give you candy for coin, daily coin ride. I'm going to tell you how many heads or tails I got. Because knowing you know about coins is probably being fair or not fair. That's your prior belief. When you bring to the analysis, you create the current belief. Now it can be informed from past data. Like, for instance, the first coin you've seen flipped. Right? So you can say, well, the only way I know about coins, it's probably going to be 50-50. Right? If I had something else that said, it's probably me pulling out a rabbit out of here. Right? Well, it's again a binary option. Very, very, very different prior on that. There's a very low likelihood to have a rabbit in there. Okay? And so the contrary with Bayesian approaches is the answer you get out can possibly depend on this prior. And so, if I think the prior age of age of life is 6,000 years, and put a very strong prior on that, I can throw tons of data at it. It'll take a lot of data to make it not be 6,000 years. If I have a flat prior, I can get a bigger range. And so that's where the controversy lies. Now, with enough data here, the likelihood becomes large enough that for most priors, it could overwhelm it. Right? But not for all priors. If I said probability of heads for this coin is between 0 and 0.1. Right? I can get heads every flip. My estimate's never going to go above 0.1. That's my prior to that uniform interval. Okay. Any questions about that? Okay. And the priors all over the place when doing these methods in a Bayesian context. Right? Who's used Beast? That's so I'm not saying. Anyway, Beast is a very popular method for inferring trees. And it has, 20 or more priors. Mr. Bayes, sort of thing, has many, many priors. He'll often use whatever the faults are. and very unlikely that your data set is the same as that of the person who first made the program. Right? And yet you're assuming that your beliefs are the same as their beliefs. Okay. So we see how those combine. So here's our likelihood for the coin flipping again. And here are different priors. Okay. So you could say, you know what, I know nothing about coins. I'll give a flat prior. And you might have likelihood if you go peek here and get back out, the same as people like. It's a flat prior. I could say, I know something about coins. Can you typically fair? So this is a prior. Okay. I need a lot of evidence to say that the coin probably has 28. Depending on how strong your belief is, you make this narrower and narrower, wider and wider. Or you could say, there's no box. I have very low, I think coins don't have many heads on them. And the scary thing is that affects the results you get. So I flip it 3 times and get 2/3 heads. With this prior, oh yeah, so probably down 0.17. Even though 67% of the time I got heads. Okay. Now again, if I kept flipping it, eventually they'll all converge. Okay. So there's probably the data over any hypothesis part. That can be intimidating. Right? Are you going to add up this across everything? And so an algorithm we use for this is Markov chain Monte Carlo, which Joe talked about a little bit. Okay, so what does it actually mean? Let's unpack it a little bit. So a Markov chain is a series of steps, and each step only depends on the current state, not states further in the past. So Brownian motion is a Markov process, right? I'm wiggling around in trait space, and I got here this way, and I got here from going this way, or I got here from coming this way. The same probability of going right next. So no matter what direction I'm coming from, I know where I am right now. Sometimes there are Markov. So I paid money for my house. If I sell my house in a year, I don't want to lose money in my house. Right? And so what I paid for it in the past affects how much I sell it for now. That's not Markov. So Markov chain just means where you go next just depends on where you are right now. That's it. In Monte Carlo, the GP is sampling from a distribution. Monte Carlo is very popular for gambling. Today we probably call it Vegas style. Okay, we're going to do Markov process Vegas style. And so now today I use the hat story. Right? So I would say, let's try to figure out what kind of hat you like. Right? So I could give you a whole assortment of, here's hats with various gradations of color, which one do you like best? Here's hats with different style of brims, which do you like best? Look at it that way. Okay? We can try to integrate that over all hat space. Okay, turn your loose in a store. So you see a hat you like better, the one you have on now, put it on. See another one? If it's a lot worse, don't put it on. If it's a little bit worse, at random, put it on. And videotape you've got into the store. Okay? So if you really like baseball hats, if you want to like baseball hats, there's some chance you could put on a cowboy hat and flip off the hat. If you really like red baseball hats, put that on. And so from looking at how frequent how frequently you're looking at different things as you go through the store, you tell us how much you like different kinds of hats. Okay. The same thing with the hypothesis space. Okay. See, we do the search across this chain to see how often we're in different states. It's by the likelihood and the prior. Okay. And that tells us how much we like it. Now, it's hard to do properly. Right? So if I put you in the store and look at you after 2 minutes, you probably still have the same hat on. You haven't had enough time to look at all the hat space. With Markov chain Monte Carlo, you have enough time to sample adequately. It could be that the hats you really love are separated from where you are now by a row of beanies. You have to cross the beanie valley to get to the cowboy hats. Right? And so we have various algorithms to help you cross these valleys and have better mixing. Okay? Most of which we don't have in comparative methods yet. We just use a single Markov chain Monte Carlo. Okay? But once you have good enough mixing, then these are actually, every time you look at something, it's a valid sample from this distribution. And so that's how we integrate that denominator. Right, other questions about that? Okay, so in the Bayesian case, how do we compare models? The AICs work, but they use only likelihood. In the Bayesian approaches, we have this prior one to bring it to. So one approach is Bayes factors. So you compare the marginal likelihoods. Just sample over all your various samples. Okay, and then we have these again rules of thumb. Okay, so strong evidence for models. So similar to AIC, greater than 10, it's a lot of evidence. Less than 10, it's in the middle. That's one approach you can do. Another approach that's hot lately is reversible jump Markov chain microprocessor. So the same way I can sample paths, I can sample models. Right? So if I can spend time in this model and play around and try different parameters on, and then I can hop to another model and try parameters on, and see if this model's a lot better than this other model. So you switch across model spaces and then we look across parameter space. Now the issue is when I first get into a new model, what are my parameters going to be? If my new parameters are always starting off with really bad values, I may not ever choose to go into that model space. So you have to be very careful to make sure you're mixing well. But if you can do that, then this is a way of integrating across those models and getting cross-state probability for a model as well as for a parameter. Any questions about that? Another approach that's popular right now is approximate Bayesian computation. Who's heard of this? A few, good. All right, and then I can also do it with likelihood too. And the idea behind this is, math is hard. So for all of us at this point, this is our old friend, right? We know what this does. We can play with it. Great. Okay, it's not true for everyone. Okay, and for some problems, there is no nice equation like that. Okay. So now what we can do is plug and chug, plug our means in here and such, and get the likelihood out. If we have no equation, how do we get a likelihood? What do we do? Any ideas? Imagine the coin flipping example. We don't know anything about how to flip a coin, binomial distribution. We figure out the probability of getting 2/3 heads. You're going to do it, right? You simulate it, right? And that's what we're going to do here. That's what we're going to do here. Okay. So we'll empirically flip coins many times. Okay. So if we said, what's the probability of heads for a coin? Well, if we know math, we could do this very fast, very efficient, right? And get this distribution. Okay. If we don't know math, or if we're working a problem where there is no such example, no such equation, right? We're going to look at evolution of traits that have character displacement. Right? There's no model for that. Right? We can imagine simulating that sort of things. And things we learned with Marguerite earlier, how to simulate grounding motion, is then wiggling around, if it gets too close to something else, it pulls away. Right? That's not part of our grounding motion model. You might have simulation like that. Right? So that's how we can get at this. Okay. So in this case, what we'll do is try a value. This is 0.2. Okay. Simulate many, many times. Okay. How often do we get our coin, our sequence back? Once, just there, right? So what's the probability of the data then? 1/10. Great. So we've done the simulation approach to estimate the probability the data is 1/10. Okay. Why is it approximate? Only do it 10 times, right? But what skill does not become approximate? Let's do it an infinite amount of times, right? So now we're going to do it that much. So that's approximate. Another issue is that here I just count exact matches, right? It's this match, this match, this match, this match. What about for our beat depth example? So I simulate GSP's beat depth. It's not going to match exactly. Right? So I know if it's matched close enough. You have a fudge factor, an epsilon. So if the beat depth is different by less than 0.01, I count that as a match. Okay. And one thing that makes approximate Bayesian computation a little controversial is this epsilon value to choose. How big a value do you choose? Another thing to think about is what parameters you're actually matching with. Right? So here I can match by the raw number of counts, but, exactly tails, heads, or I can do the proportion of tails and heads, or I could do, only the third number that comes out. In the GSP's case, grounding motion, I could simulate data and see how often I get exactly the same values. I could do it and see how often I get exactly the same ancestral state. Okay. There's different ways of summarizing your data to put into this. there's a lot of choice that comes into that process too. We'll get into today. Okay, and there actually are ways to choose which some of the statistics matter most. That can also affect what answer you get. Okay. So you want a number that can give you lots of information about your data to calculate. Okay, let's try this. So here I tried 200 simulations for each of these values. Figure out how often I got an exact match to the sequence. There we go. There's a Bayesian computation in action. It's really rough. Okay. So we can do more. I've done 2,000. Better fit. 20,000. Better fit. And 200,000. Better fit. Right? And so without actually knowing any math, just knowing how to simulate, you can actually estimate this likelihood. What is the Bayesian is what I'm going to simulate from. So what I'm actually simulating from here is a uniform prior. So if we tell you 50% of the same. If you got a different prior, an exponential prior, I can simulate from that instead. So that would be my prior, and then the numbers I get out, this curve I get back out, would be the posterior probability. Any questions about that? Yeah. Really something to be you have to have some sort of model to run the simulation, right? Which need not be an equation. I could, create a coin and different weights on each side or something for that, hard coin. So it doesn't have to be mathematical, equation to do it. That's some way to simulate. Question. Other questions about this?
So about this model average parameters. So if you really believe that there's something that said at least one of these models is way better than some of these other models, and that some of the models are really bad, why would you want to average those effects in?
Right. So if you have a model that is really awful, you might throw that out. So I found, for example, we're looking at an extension to MESI, which is looking at discrete traits of evolution and looking at how they affect diversification rate. And some models are too complex for the data, so you get very, very bad estimates. If we do, 0.1% on that rate, and that rate is a billion, and everything else is a much smaller rate, even though you're weighting it down, it still has a pushing effect. So yes, it's some nuance. You might need to exclude it really bad. There's no rule of thumb how much you have. So in some cases, you have always putting the data on one model and the other model, instead of drop proof from that. Certain model choice.
You don't simply use the same model. Use the first view of time, or second, or other systems, and then averaging into just what is wrong.
Other questions about this? Exactly on time. So now you have time for discussion about this in general. So now you can sort of understand likelihood versus Bayes versus approximation. Also, you do approximate likelihood too. Just take out the prior. So for your analysis, when you go home, you're going to have your data to look at. Oftentimes, you have a choice of methods to use. What are you going to choose? Try.
What I would do, I would have a model what are, just, yeah, depending on what tools you want to use.
That's good. So like, yeah. So if you have a model, do not do approximate Bayesian computation. Right? You can just plug and chug an equation. Don't simulate 200,000 times instead. I'm just not sure about the equation. So that's one decision point. Okay. Now, assuming we have an equation and we can do likelihood or Bayesian approach, what are you going to do?
If you got enough ability in the job, which things as well, you can do that as this would be knowledge about probability. So most of the times artificial distribution is
Like generally true, but not always. So if I have this sort of likelihood surface, here the maximum likelihood value is right here. If I imagine a uniform prior, most of my weight, my posterior probability, is between here and here. And so the Bayesian estimate would be, this plus or minus this range. And MLE would be this plus or minus what we have to get down to go, up to like so you get very good estimates from that place. Those might be free component places,
It's very bad.
right? Have you met your data? Yeah, right. And so generally you hope it's a nice intermodal distribution. It need not be. And then it doesn't matter. Now in the world of finding data, once you have enough data, it won't matter. We're looking at real evolution, there's so many ways. And it doesn't matter.
So hopefully your posterior though would have that whole physical piece of it.
Well, I can make this peak arbitrarily narrow. I can make this
Right.
about 1%
But-
distribution.
But practically, yeah, it would have difficulty visiting it, but you would still be able to see that would be there and spend time with it. So you would have that, you have the distribution, and maybe your summary statistic would indicate that, but you would still be able to see that.
Yeah.
Look the whole bunch.
And it isn't one of those good points. And so it also helps to visualize what you're looking at. So visualize your raw data, but also visualize the structures you're looking at. So something we do in our lab is, create a contour plot where we have, here's our alpha estimate, here's our sigma squared estimate. Alpha, we find the MLE is here. You might try a bunch of values around it, and then build a contour map. Okay. There's a shortcut to figuring out the uncertainty. Once you're able to visualize the space, and you'll find out, oh look, there's actually a ridge or something like that. And same thing with Bayesian function, you can adapt posterior probability density, you should map that density and do that. You spend years getting your data, spending the half hour of life. Other people thinking about this. Do you make a choice? Do you do both? You try some priors. And so then people sometimes do change their priors. They run the data set, find this is a good prior, we change the prior. Which philosophically is kind of weird. Okay, look at the data, let me go back in time and change what I thought about the system and go back and change it again. In practice, maybe help you in your analysis.
In that case where you're varying the prior, how would you decide which is the best option?
This is one data in the past, what have you done?
We could run a bunch of courses from PhD.
Right. So that's what robustness, right? Yeah. So same way old school, doing non-parametric statistics, doing parametric statistics. So you could, and then the same things are fine. If you don't,
If you didn't have a prior or you got confident on the prior, would it be acceptable to divide, if you had large enough sample, divide your sample, estimate the prior and estimate test level
So, no, that's really fine. It's sort of also a sort of empirical Bayesian approach where they get prior from the data, and that's accepted too. But also we'll try to look for unformed prior. Right, so the coin flip example, if you don't know anything, you say okay, from 0 to 1. And all that helps you then is select overall. And that can help in some cases, but in some things like tree branch length, there's no unformed prior. Right? Say it goes from 0 to infinity, well, it has an exponential distribution, fine, but then how long is that? Question. Other questions or thoughts about this? Okay.
Can you talk a little about information criteria?
Yeah, this is the various alternatives to AIC. So the BIC is one, the BIC is another. I don't know enough to say what the development how to approve them, but what the merits I don't know. Anyone else can curious now? So I know I was talking to Ken Burt at one point about using AIC between homogeneous, and he said, yeah, BIC would be better if you get the using it. One data. I think AIC can choose more parameter-rich models than BIC does. There's also AICC, which is AIC corrected for your sample size. AIC, drive various approximations. And so you can put in some sort of AICC.
So it's been not enough that I've forgotten some of the details, but there's a nice couple chapters in the very largest, at least the AIC and BIC. And so the AIC, as I recall, is based on the
What tools are you using?
yeah. I don't think there's and I think there's well, maybe we don't know. You should definitely look at it. But and so the EIC or short information theory, I can't actually but there's concern that it's really and it's also not as closely it's not going to be truly
And what about these tools that would include distance and pilots and triangle topology? I just had a big population, I don't remember part of it, dealing with they looked at AIC as an estimate for this tail distance for the 500 model selection space. Found it really doesn't fit in that. You can actually estimate tail distance directly for your simulations. Well, right, no, but you hope that if I know the truth, then this measure gives me the estimate of the truth. If it doesn't, then
What's your experience with ABC for pathology? What kind of samples are these?
so we have something where this you know, the features now, where it'll allow an arbitrary model to be created by a user. So here he can say he discrete time step arbitrary. So it could move by a random normal, right? This will be squaring motion. It could move by a random normal that is displaced by a year. So it's like squaring motion has displacement. And depending on what parameter in the model, what some of that's already, what that some of that's already carries, right? So if you want to get a good estimate for the social state, a good summary stat is the mean of the place. If you want to look at the rate, then that gives you better information compared with that, you know, the difference between the values. If you write something that's I wasn't what use ABC much yet. There was one approach to putting it better. The one approach to estimating, it was estimating rate spreading motion and had some data. I forget what some of the estimates in that case. It seemed like it used a lot. But it used a lot more biology, obviously, looking at the various parameters of the sequence. Good questions or discussions about this? And part of it would be the limit deciding between Bayesian and likelihood. It's not based on philosophy. So the problem is not the figure is information.
Well, I think people choose between Bayesian and likelihood for all sorts of silly reasons. Like there's a semi-silly reasons like I've got a fast program for this, or I know how to use that. My friend used it and got trained. But it strikes me, it's always struck me, that the difference between them is really a matter of philosophy and science. And I could argue that Bayesian inference has some sort of assumption of consensus reality that other methods don't. So the fact that I can produce prior on a parameter, and that when I publish the paper and say this was my prior, I'm kind of implying that that's your prior too. And to the extent that that's what that implies, I'm assuming that we all live in the same consensus reality, and we all choose, we can reasonably be expected to all choose the same prior. Anyway, I think there are issues at stake here much bigger than whether this program is faster than that program. In practice, people choose for all sorts of haphazard reasons.
Yeah. And what would you argue people should do?
We should do? They'll do it my way. No, I think in practice, when we go to cross the street, we're all Bayesians. We all go to the prior. Is there likely to be a car coming at this time of day? Not. We listen for evidence based on that. And various penalties, like a much bigger negative penalty of getting hit by a car than on not crossing the street when we could have. And we put that all together and make a decision to cross the street. And many people say, okay, that means you're Bayesian. No, it doesn't. Only become a Bayesian when you make a choice among, you use a controversial prior and report the conclusion, at least in use in science, in situations where you're kind of assuming that everybody else will like your prior. Now that may be too restrictive a definition of Bayesian.
I mean, a lot of people are empirical agents. Well, data to, for example, if we're estimating ancestral states for discrete traits, right, with likelihood, we assume like an uniform prior figure or something like that, effectively.
I mean, you can do a lot of these things as ad hoc techniques. And you can formulate some of them where first we estimate something, then we put it in and it generates our prior. Or you can push it back a little and have prior on that prior parameter. Then you're back to being a Bayesian and so on. Yes. I think when we cross the street, we're all Bayesians, but we don't all use the same prior.
You've got most of the vast majority of the application of basis requires all the flag open meetings matter.
That-
The rarely times something is really a guy. If you apply it wrong, because it's necessary for the business function of God, because that actually requires them forming because in the vast majority
But in phylogenetics, it's not the case actually. So I mean, so we've had lots of examples where, you know, for Mr. Bayes, it changes prior on branch lengths from a uniform to an exponential, and affected the posterior probability of clades by a lot. In the sort of the OUBM world, you know, we're working in areas where the delta AAC is like 2, 4. So it's not a lot of likelihood of getting information, and so the prior there will have a good effect. Yeah, I know.
I think in phylogenetic inference, priors on, say, topologies, tree topologies, don't matter terribly much. But priors in branch lengths can matter a lot. And I still think, I'm still worried about things like priors and covariance matrices. I was getting at this and speaking, where they build in how much interaction they expect between a random gene and a random other gene. And some people will say everything interacts with everything. And some people will say, no, it's very sparse. And I think we can come up with very different priors and get very different inferences out.
If I answer all the questions that you said about the difference, if you were to have a prior that said, I have a uniform belief from there's all diagonal elements are all 0, the all diagonals are all 1, and you have that the range of knowledge of the full array of covariances, would you accept that as something that would be appropriate?
If your prior were assuming that all the off-diagonal elements are always exactly the same, it would be very restricted prior. You mean separately in each one? Well, you probably have to go, I mean, for covariances, you don't just go from 0 to 1 anyway. I think that priors that say took a random covariance matrix orienting axes at random in space and so on, and choosing distributions of eigenvalues that are maybe exponential, would generate matrices that have a lot of interaction among a lot of loci. Many loci interacting with each other. Other people's priors would be on some kind of randomly connected gene network where each gene interacted with only a few other genes. And I think those are very different. They're different views. At least at this stage, if you can't choose among them, you'll end up with some people drawing very different posteriors because they're using very different priors.
One jargon note, so you mentioned hyperprior. Right? So in the quite open context, you have a prior on priors. You don't want to specify what your prior is for something. You can put prior for that. There's discussion points on this. So one good use of this Bayesian approach is sort of a meta-analysis, right? So we have the field thinks this about some parameter, and we can quantify that as a distribution. Then how does my data affect that? Right? So I think that, you know, Amberella assisted all our angiosperms with prior probability from all those other studies, posterior from other studies of 55%. Then how does my new data set change that belief? So you can see it being used in that way, but often not. We don't use C data sets to get prior. It's sort of pulling out of the air. So I know I'm clear about this.
In response to what you just said about using existing data sets as your prior, if those data sets, when have been occasionally extensive comparison, then you're accepting
Or if you're not building someone, you just read a paper that uses Bayesian analysis, you believe it, and you're also thinking about the values. Yeah. Those are people who don't think about what the flowers should be. So I did an analysis of people who do tree influences in flowers. And out of like 90 papers I examined, only a few actually mentioned flowers, only 2 actually changed them. Everyone else just had the same default flowers. For males to flies to all angiosperms. A user is a believer.
I have a worse example of the 3 major papers in the late 90s that introduced Bayesian inference in biologies. They all mentioned that they had priors, and they got, and all the papers got heavily into the Markov chain or machinery. 2 of the papers failed to tell the user what priors they used. Those are from the introductory papers of the method.
Those people are Bayesians. On the other hand, I mean, sometimes priors can help restrain crazy value, right? So you're looking at something that has, not a lot of information, and it's bounded from 0 to infinity at the rate. By adding a prior, you can sort of keep it in reasonable areas, which would be good if you can estimate it for something that matters, but still doesn't require to matter a lot. Yeah.
That's when people make assumptions too. One of the assumptions is that they just like we're definitely putting out a lot of philosophy of Bayesian approaches, but I think that also if you look at the assumptions that are in the are maximum likelihood estimates, then they would be violated as well. So it's you can do good and bad with both.
The Bayesian approaches rely on likelihood at the core. So if you don't believe Brian Motion is a good model, the likelihood works equally bad for Bayesian approaches too. Now there is an assumption of
Just agree that all the assumptions of likelihood methods are also in corresponding Bayesian methods. So there is no assumption in the Bayesian method, in the likelihood method I know of that isn't also in the corresponding Bayesian.
Except for this case, right, where Friedrichs want this, Bayesians want this. And so that is, if you care about what's the best value optimizing all the parameters, you care about what's the best value integrating with all the parameters. So that is